So in today's lecture, we'll look at NATs, IPv6, and then get to multicast. I'm not sure how much we'll cover of multicast today. How many of you have heard of NATs? Do you know what NATs are, what they do?
It is between the subnet and the public internet. So that in the subnet, the IP is using start with 172.60 or 91.92.168, and when you go through the gateway, it transfers into unique IP and go through the internet.
So what's the motivation behind using a NAT?
That the IP address for internet is not enough, so NAT.
So the IP address, we should be careful. We should say that IPv4 address space is not enough. In IPv4 you have 2 raised to 32 unique hosts possible given the address length. Now we already saw in the last couple of lectures that the way these addresses are allocated, it's not very efficient. If you did class-based addressing, you frequently run out of networks of different sizes. CEDAR addressed that issue, but even with CEDAR, the allocation is not very efficient of IP addresses. There are a lot of holes in the IP address space, and even if there were not holes, even if there were no holes, the number of addresses that are available to begin with is not very high. So there is a scarcity of IP addresses. So NATs and IPv6 both try to address this scarcity. Now NATs, this slide explains the architecture behind NATs. So what NATs lets you do, it will let you share one public IPv4 address between a number of different machines. So you have a number of different hosts. All of them will share a single public IPv4 address. Internally, they'll have different IPv4 addresses, but the IPv4 addresses that exist behind a NAT are all private addresses. So private addresses the most common ones are these two networks. So what you can do is you can create a local network, assign these addresses to machines in that local network, but these addresses cannot be visible to the public internet. These addresses are reused over and over again. Any other IPv4 address, which is a public address, cannot be reused. Once it's assigned to a host on the internet, then it is unique. It uniquely identifies a host or an interface on the host. Whereas these private addresses can be assigned to multiple machines. And NATs is a way to make this whole thing work. So one of the motivations behind NATs is that the address space is scarce, you are running out of IP addresses. The other thing is that when you subscribe to an ISP, you are typically given only one IP address. That is related to the fact that IP addresses are not plentiful. ISPs themselves have a limited amount of IP addresses available. So to each subscriber, they'll assign only a single IP address. But subscribers, on the other hand, might have multiple machines that want to connect to the internet. So on your home network, you might have different desktops, laptops, all kinds of devices. All of them want to connect to the internet. But your ISP provides only one IP address. So NATs are a solution in that scenario too, where you want to connect multiple machines, but you have only one IP address available. So how do NATs work? So NATs work through a NAT capable router. So there is a device which divides the public internet and this private network, and this device implements the NAT protocol. The NAT stands for Network Address Translation. Within this network, all packets that go to this network or go out from these machines will have the private IP address. So all packets floating inside here will have the private IP address for these machines. As soon as these packets leave the private network, this NAT box will translate these addresses into a public IP address. That is the basic job of this NAT box. It's going to translate these private addresses into that single public address that's been assigned. So how would this work? This is the motivation for NATs. In the implementation, at the NAT router, every outgoing datagram, you're going to replace the source IP address and the port number to the NAT IP address and a new port number. So you have a NAT box and you have different machines connected to this NAT box, and these machines are trying to contact something on the public internet. So let's say there's a server. Now this workstation, let's say there's a browser running here. It wants to connect to a web server here. What does the IP packet which carries the HTTP request look like? Yeah.
Private address of the machine. So
You'll have a source address and you'll have destination address and private address that says 10.0.0.1. Destination address is some public. Okay, this is the packet which is inside the network. Now in the IP headers, do you have port numbers? Yeah. You don't have port numbers. So that's one problem with an architectural problem with NATs. This router, in the layering principle that we saw earlier, every layer works independently of the other layer. There is some connection, but there should not be any layering violations. So what we learned earlier was that the application layer and the transport layer runs at the end host, and the networking layer, data link layer, physical layers, that runs everywhere, including the end host and the network. Now to get the port number of this packet, this NAT router has to go and look at the transport layer header. So this portion of the IP packet, which is data as far as this router is concerned, to implement NAT, it has to violate the layering principle. It has to look inside the data, look at the TCP headers, TCP or UDP headers, and in that data region, it will locate the port number. So port number equals X. The destination port number doesn't matter here, but the source port number is identified, and what the NAT router next is going to do next is when the packet is released onto the public internet, this packet is changed. Now your source IP address becomes whatever is the NAT IP address. Let's say this box had the source port number, which it got from looking inside the transport layer header. So the data here. It is changed to some Y. It's not the original port number. And then the destination address and destination port numbers remain the same, and then this packet travels to the server. Now how is the server going to respond? Yeah.
It'll send it right back to the NAT.
The server is going to look at this request packet. It will look at the source address. It will look at the source port number. So the socket is as far as the socket is concerned, this is the port number. So now in the reply packet that is sent, the destination address becomes the NAT address. The destination port number becomes the port number that was assigned by the NAT box to this packet. Once this packet reaches here at this NAT router, then the NAT router is going to do the translation again. When it made the original translation, it will create a table which will map this private IP address and private port number onto the public IP address and a different port number. So depending on the port number, it will uniquely identify which machine was sending the packet. Yeah.
You know, 3 machines are talking on the HTTP port 80, right? So 3 machines all send, or for some reason or another, let's say they all have a source, I should say, a source port. That's all the same.
Source port can be the same. See, your translation is going to happen so you're saying that you have 10.0.0.1 and you say that the packet that goes out has the same source port number. The OS chooses the same port number. So source port number is 1345. So the source port number is the same here, but the key that this NAT box is going to use to identify this packet is not only the source port number, but the source port number and the private IP address. So by using that, the combined tuple, it can distinguish between these addresses. So now when the packet goes out, it will assign this port number, let's say, to some X, Y and Z, which are different. Now when the reply comes, the reply will come to either Z, Y or X with the public IP address. Now depending on whether it's X, Y or Z, it can uniquely translate it back. So that is not a problem. Yeah.
What happens in the scenario, the same computer has multiple copies of the same application running? And can those applications have the same source and the same port number? Suppose multiple browsers.
That's a violation of creating the socket. Right? If the socket is already bound to a particular port, the operating system cannot allocate that port to another socket. That's not a concern here. Yeah.
In this case, we can have only the private server.
Yeah, you cannot have servers running. With some hacks, you can have servers running inside the private network. So why can't servers run inside the private network? Right. So suppose your web server was inside this NAT box. Now the web server is running on a well-known port. If some machine from outside tries to connect to this web server here, it's going to send the packet to the public IP address and it's going to send the request to port 80. Right? So the only way it could work was if this translation, that X was also 80. Right? If you configure the NAT box in such a way that port 80 from this particular machine is translated to port 80 with the public IP address, then in that scenario maybe you can run servers. So to run servers within a NAT box, you need cooperation between the NAT box and the machines. Now typically NAT boxes are something that you buy. You cannot configure what the table entries would look like. They are not related to the machines that are sitting behind the NAT box. Yeah.
Port forwarding figure that's how the port forwarding does, so you figure your NAT box set up so you just identify ports and they'll always go to a certain computer.
Right, so that's what I meant by cooperation between the NAT box and the network machines. The other problem is that you can only have one server running. Right? Now suppose this machine also wants to run its web server. Then you're stuck because you have already allocated port 80 to this other machine. Yeah.
It's like a big security problem if you just have a box somewhere that you just change, the source, address, and port, and then just collect. If you somehow intercept packets going one way and change the information about them so that they'll come back to you. Isn't that
That problem exists. Yeah. But that's not specific to NAS. I mean, you have to trust routers or boxes that are in your path to any destination. That architectural problem is still there. But you can reduce the amount of information that is exposed to those boxes. So you can have all the data which is here is encrypted. Yeah.
Why can't you have two web servers? So then the other web server have different IP address. Even if it has the same port, so how does it matter?
But how would an external machine connect to the different web server? See, the way you differentiate these two is by assigning a different port number, right? They have different IP addresses, fine. But once you assign a port number, now you assign 80 in the translation table. So the outgoing packet for this machine, port 80 is translated to port 80. So what happens here? You cannot again assign port 80 to this machine. X and Y have to be different. Look at it this way. A server here, no, a client here sends a request on port 80 to this public IP address. Where would the NAT box forward that request? It will forward that request by translating this 80 to the port and IP pair, port and private IP pair, because you have already assigned 80 to one port IP pair. You cannot assign 80 to another one. Yeah.
If you have a cluster of web servers, it's much easier to just load balance from the other ones.
If you have a cluster of web servers,
Let's say 5 is listening to 14,
Mhm.
it's up to the NAT box to decide
that's a load balancing mechanism. Yeah, that's running on top of NAT. If you didn't have load balancing mechanism, what do you do? Then you have to make a choice. And again, the cluster of web servers is really one web server as far as the outside world is concerned. It's serving the same set of web pages. So even though you have physically different machines, but the service that it's offering is still one service. So this explains the process. Step by step what happens with the NAT box. Any other scenario where NATs could be a problem? Yeah.
That has each computer inside the network has 0 to 65,000 ports. The NAT has to divide the port range. The NAT box has to divide the port range. It goes to the center.
So the port range reduces, but you have to be a little bit careful there. So unless all of these machines are using all the 65,000 ports for different sockets, which they can't. I mean, you run out of resources faster than you run out of port numbers. The limitation here is only the sum of all the sockets that are being used. If that's less than 60,000, then you're fine. If you have all the computers, then you're likely to run into problems. So NATs are a solution only for small networks. The other scenario is, even if you don't have well-known servers, suppose I mean you're running a peer-to-peer application, In a P2P application, nodes will exchange information, and then depending on where a file is located, a client machine is going to initiate a connection to the server machine where the file is located. If your server machine is behind this NAT box, you cannot do anything. Right? How do you initiate a connection to the server machine? You're sitting outside the NAT. You know that some file exists here. How do you go and access this? Again, there are sort of hacks that let you do it. Both of these machines can contact a third machine which is sitting outside the NAT box. And the client machine will ask the supposedly server machine to initiate the connection. So all machines outside sitting inside the NAT box have to be talking to some machine, some client machine, some machine sitting outside the NAT box. Whenever a connection has to be initiated from outside to in, the way it's done is you send this message to the machine sitting outside. That machine tells the machine inside the NAT box, because there is a connection existing, that you initiate this connection. So NATs have architectural problems. And one of the principal reasons NATs were introduced was due to this address shortage. And it's been argued that the address shortage should really be solved by IPv6, not by using NATs, which are a hack, which violate some architectural principles and cause problems, and it's a solution that does not scale well. Yeah.
If a inside network connect to a server outside network via a TCP connection, and will the NAT box reserve the port number for this?
NAT box reserve the port number.
Yeah, because it's a TCP connection.
Yeah, it will. I mean, the NAT box creates a table, and it reserves that port number as long as that connection is alive. Yeah.
Can only get one IP from ISP.
Yeah.
So even we use IPv6, we still want to use NAT.
Well, if you have IPv6, then ISP will be more liberal with it.
But how if users apply for infinite IP from ISP?
They cannot apply for infinite IPs. Yeah, so I mean, the IPv6 will increase your address space. It won't make it infinite. So there will be still some constraints, but those constraints are much looser compared to what you have now. So the background for IPv6 is that, I mean, IP has been patched with subnets, supernets. We saw those solutions earlier. And then there are solutions like NATs, but you still have this fundamental problem of the 32-bit address. That's very small. So in the early 90s, IETF foresaw that we're going to run out of addresses soon. So you need to change IP. Now, because you need to change the address space from 32 bits to something higher, that meant that this would require a change of header. So once you're going to change the header, the IETF decided to make other changes to the IPv4 format, and other changes were introduced besides the simple increase in address space. So other header format changes help speed processing and forwarding. We'll see how. There are fields in the header which help facilitate quality of service. And the IP header has now been fixed to a 40 byte length. Earlier, you could have a variable length IP header by including options. But with IPv6, you have a fixed length 40 byte header. So why is a fixed length header of any importance? Yeah. Exactly. I think if you know the size of the header exactly, it's much faster and easier to process rather than having to guess. If the size of the header is unknown, then processing becomes slower because you don't know how many bits you have to process. Scheduling becomes a problem. If the size is fixed, then you can process it faster. The first version of IPv6 was proposed and completed in 1994. Some changes have occurred since then. IPv6 is still not in use. One of the reasons is because of NAT. NAT gave a solution which let the internet grow. And then there are other issues. Yeah. Europe, not Europe, but Asia, Japan especially, Japan, Korea, they are moving very fast to IPv6. Europe is faster than the US, yeah.
You know, it's like two machines, one using IPv6, like communicate with IPv4.
I'll come to that. It's not backwards compatible directly, but there are techniques that let you use both. So the IPv6 header looks something like this. Similar to the IPv4 header, you have the version field here. You have priority bits here. Priority bits are similar to the type of service bits that you had with IPv4. And then IPv6 introduced this notion of a flow label. Now this goes slightly away from datagram mentality, where each packet was treated individually in the network layer. Here, you can identify datagrams which are part of the same flow. But what IPv6 did not do was define these flows precisely. So these flows could be part of the same TCP connection, or these flows could be all the flows coming from a particular network, particular subnet, and depending on the flow and priority, routers on the path can give different types of service to these packets. So IPv6 has identified these fields, but precise implementation has not been defined. The source address is 128 bits, the destination address is 128 bits, up from 32 bits. Do you see anything missing here from the IPv4 address header? Yeah. Options, well, so the options are missing, so that makes it a fixed length header. Another thing that's missing here is the checksum field. There is no checksum field here because, I mean, checksums and error detections are done in all sorts of layers. Doing it in IP doesn't give you much, and it speeds up processing. It's one less thing that a router has to do when doing the forwarding. The checksum has been removed from IPv6. One of the obvious gains of going from 32 bits to 128 bits is having a much larger address space. Can you think of any security gain of going from 32 bits to 128 bits?
if a autonomous system is assigned a larger range of addresses that are more sparsely populated, then they'll be able to better implement scanners on some of the unused addresses for worms and things of that nature.
Who would be able to?
The autonomous system.
You're close to the answer. The way a lot of these worms propagate, I mean, if you put up a new machine on the internet, you give it an IP address, within seconds you'll see that it's being scanned, port scanned by attackers trying to break into the machine. Why can the attackers do that? Because the IP address field, 32 bits, is packed. It's very dense. The addresses have been allocated. Besides being dense, it's also small. So these attackers will randomly scan IP addresses and see if a machine exists and if there's a vulnerability. If you have addresses which are 128 bits long, then random scanning is impossible. If you shoot in the dark, if the room is full, you're likely to hit someone. But if the room is completely empty, shooting in the dark is not going to help you. So by increasing the address space, these random scanning strategies are diminished. Yeah.
But also most of the worm detection techniques rely on people making false states to unused IP addresses. So now you have a larger range of unused IP addresses, which means you can probably pick up a worm attack faster and react to it faster with more densely populated address space.
I'm not sure if I agree completely with that, because even with IPv4, you have these unused spaces, right? Now, because the address space is small, these worms are more likely to hit that unused space with IPv4. With IPv6, you have this huge range of unused spaces. But because the space is so huge, a random hit will not land into this unused space that you're using to detect.
But isn't that how best detection is done, by looking for scans of unused ports and IP addresses?
Right.
So now you have a wider range of unused IP addresses, so you'll be able to do detection potentially more efficiently and pick up a worm faster than you could.
So for that you have to keep track of all the unused space. So you can do two things. You can either keep track of everything that's unused, or you can monitor parts of the unused space that you have decided to use. So there's a difference between the two strategies. If you're just looking at a certain portion of the unused space, then the problem doesn't get any easier. But if you're monitoring the entire unused space, then your processing becomes harder. Right? Where do you monitor? That unused space packets, how are they routed, where do they go? So it's a little bit complicated there. So what does an IPv6 address look like? You know, it's 128 bits. The allocation is classless. So you don't have class A, class B, class C kinds of addresses. The prefixes of those addresses specify what kind of use that particular address is. Now unicast and multicast we saw with IPv4. Class D was a multicast address. IPv6 also has an anycast address. So anycast is, you can think of that as a mixture of multicast and unicast. With an anycast address, the anycast address is allocated to a number of different machines, like a multicast address. But as opposed to multicast, a packet which is sent to an anycast address is just sent to the closest machine which has that anycast address. In multicast, which we'll see later, anything that is sent to a multicast address is sent to all machines that have that address. In Anycast, any packet that is sent to the Anycast address will only be sent to the nearest machine which has that address. So things like load balancing you can implement with Anycast. You can implement DNS servers. Lots of different applications exist if you have this Anycast going.
It's always the closest thing to Dallas.
I'm sorry?
It's always the closest server.
So again, closest is undefined. It can be, it's left to the router to decide which is closest. It could also be the least loaded. But the general principle is that you have a cluster assigned the same address and you're going to send the packet to only one of them. The standard representation is 8 16-bit values separated by colons. So IPv4 address was a dotted quad format, 128.59.x.y. Here you have 8 16-bit values. So it looks something like this. Often these addresses will have a large number of zeros. So you can compress the zeros by just having colons where there are no significant values. Slash notation is the same as v4. So if you have an address of this form /40, it indicates there's a 40-bit prefix. This is describing a network with a 40-bit prefix. So it is the same idea as IPv4. X/y, y will define the length of the prefix. Yeah.
Separate the addressing.
Any concrete reason? Well, just one thing is you want to remove any confusion between IPv4 and IPv6. So granted there are more values here, but it just looks different this way.
Identify a port before an address.
I see what you're doing.
Well, that could be a problem. But typically, you define port numbers by you have port numbers associated with names rather than IP addresses. So this is for human readability, right? I mean, it could get to be a problem if all your last bits are, or all your last 16 bits are 0. So you have colon here and then the colon port number, but that's not a big problem. Yeah. So there was a version 5 which was proposed after version 4, and it was called IP, I think ST, and it was supposed to support media streaming, quality of service. Then there was another protocol which was proposed, which is called Wrttp, which did the resource reservation, and that took over all the functionality of IPv5, and IPv5 quickly died. So was that your question? Why is the 5 missing? I'm sorry? Was your question IPv6 or whether?
In this version, there's too many IP addresses.
128.
Yeah, you're
Memorizing this is not a good idea. But you need this large address space for a variety of reasons. You don't want to run out of IP addresses. I mean, people say that, every cell phone, every watch, every toaster will be on the internet. So you need IP addresses for all of them, although I don't know what a toaster is going to do. You want to come up with one design and you don't have to redesign 10 years from now, 15 years from now. So you increase from 32. Choices where you go to 64, 128. Because you also have to look at the bit, the word boundaries. So 128 was a large enough choice. It gives you a lot of flexibility. Yeah. I don't want to go there. Google is what? 1 followed by 100 zeros. And how much is that 2 raised to? With 2 raised to 128, every grain of sand on Earth will have its own, probably subnetwork. So the address prefixes look something like this. The important thing to note here is the unicast address space. So every unicast address on IPv6 will have the prefix 001. And then the addressing is similar to CEDAR. So first you identify that this address is unicast by the prefix. Then you look at the internet as a hierarchy of networks. So host interfaces will belong to subnets the same way they do with CEDAR. Addresses have the subnet prefix and a host identifier. So subnet prefix x/y, and everything from bit y onwards will identify uniquely the host. The subnet prefix structure worked well with CEDAR. It allows you to aggregate into larger networks. Then another idea of IPv6 is to have a provider-based plan of allocating bits. IPv6 defines 3 levels of hierarchy. You have region, so region could be North America, Europe, Australia, East Asia, provider, and then subscriber. And the goal of this is to reduce BGP overhead. When we saw in the last couple of lectures how complicated these BGP tables can be, how the prefixes, how you can have holes in the prefixes, and you need to do longest prefix match. You have to fill these holes. Forwarding decisions becomes complicated. You want to simplify that, and you want to aggregate routes, especially for BGP. So a provider can aggregate a single prefix for all its subscribers. So you have 24 bits for providers, so there are 2 raised to 24 providers possible, and each provider can have 2 raised to 16 subscribers. So you allocate 16 bits for the subscriber. Region is 13 bits. So that also makes forwarding decision very simple. If regions are well defined by these bits, then you get a sense of geographical routing here. The way addresses are assigned with IPv4, the bits don't mean anything geographically, whereas routes often get aggregated geographically. So the forwarding decision becomes much simpler this way. So a typical IPv6 address, unicast address, will look like 001, region ID, provider ID, subscriber ID, the subnet that the subscriber has, and then finally the interface. And the interface bits are also related to the interface card that you use, the MAC address, and we'll come to MAC when we get to the link here. There is one problem with IPv6 addressing, and that's of multi-home subscribers. So like machines on the Columbia network, we are multi-homed. We have one connection from a provider of the commercial internet, which is Broadwing, and we also have a connection from Internet 2, the educational or the research network. and the way IPv4 addressing and BGP and forwarding works, the single address works well for, is sufficient for different number of providers. But with IPv6, if you're multi-homed, you have multiple providers, then this field becomes problematic. And people are actually working on solutions, clean solutions to enable multi-homing with IPv6. And anycast addresses are just like unicast address, and closest is not well defined. It's left to the routing infrastructure to decide what closest is. Now IPv6, the first implementation came out in 1994, but it's still not been deployed. Why? Because deployment is not very easy. You cannot have a flag day. Okay, 5th September 2005, everyone is moving to IPv6. That you can't possibly do. So you have to do a gradual deployment, and gradual deployment becomes very problematic. So for a period of time, you need both IPv4 devices and IPv6 devices to coexist. And there are two ways to do it. One is the tunneling approach, which we'll see in the next slide, and the other is a dual stack approach. In a dual stack approach, nodes will run both IPv4 and IPv6, and they can be assigned a v4 compatible v6 address or a v4 mapped v6 address. So suppose you have a 32-bit v4 address for a device. You can just add 96 zeros and make it a 128-bit address. Other addressing schemes are where you map a v4 address to a v6 address. So in a dual stack operation, these nodes can talk both IPv4, IPv6, and depending on who they are talking to, they can do the translation. Tunneling is something more interesting. So in tunneling, the logical view is that you're running in a network where some devices understand IPv4 and IPv6, whereas other devices only understand IPv4. So with tunneling, you create a logical tunnel between devices that speak IPv6, and this tunnel goes over devices that speak only IPv4. And the way it's done is, in that tunnel, you're going to encapsulate your IPv6 packet with flow ID and source and destination, whatever, into an IPv4 packet. This IPv4 packet flows between the endpoints of the tunnel. So router B and router E both understand IPv6, but routers C and D do not. So you're going to create a connection which goes from B to E. This connection is IPv4, and the routers in the middle which understand IPv4 will then forward these packets along as if they were IPv4 packets. At the end of the tunnel, router E will then extract the v6 packet, throw away the v4 headers, and then forward that packet along. Yeah.
Address in the 32-bit space, right? Or no? So that's what
No. See, you cannot.
If you're talking IPv6, then you'll only talk IPv6 to another IPv6 machine, right? So there's one more machine at the end of this connection which speaks IPv6. So what you have here is the router view, This could as well be an end host view. So when you make the connection to the first IPv4 machine, what you're doing is you're creating this tunnel. I'm sorry? So you said what happens when you make the first connection. So what do you mean by the first connection? Right. So V6 is talking to V4 using a V4 packet. And that is done by creating this tunnel between two V6 machines. Source is B, this is a V6 machine. Destination is E, which is again a V6 machine. But the red packets are V4 packets. So both B and E understand when the tunnel is created that what we are really carrying is IPv6 traffic, and when E receives this packet, it will extract the V6 packet and then forward it along. Yeah.
Service or diversion field, so that you're able to recognize that pass down inside.
Right. I mean, both B and E have to be aware of this tunnel. They have to be aware that the packets that are coming are tunnel packets. There are different kinds of ways to implement that. Yeah.
It has a considerable
Amount of overhead.
So things
Things do get slowed down. So until everyone moves over, you have to live with that. Yeah.
When it sees that that packet needs to go to destination F, that's what I'm wondering.
no, router C never sees F.
Router C sees destination as E, because this is data for router C. It's not going to look inside. The only header that it sees is this E. So, yeah.
Make a decision about where to send it based on what E is?
Yeah.
But isn't E an address in the 6 space?
E speaks both.
6 and 4. Right? I mean, if you don't speak both, then there's no way you can talk to each other. So there have to be some machines that speak both and can do the translation.
That means the routers have to know what the other routers, what kind of language they speak, version 6 and version 4.
Yeah.
And based on that, you have your different addresses.
Right.
And similarly, like A will have to know whether B speaks IP version 6 or not in the router table.
Yeah.
Or any format.
Yeah. So you create this tunnel when you realize that the chain is broken somewhere. Same question. Yeah.
Yeah,
So like, I mean, to go to Australia on IPv6, you have to go through a tunnel. The link to Australia, both ends speak IPv4. Yeah.
what will happen is the IPv4, but the machine between these two ends is IPv6.
So the machine
At the two end is IPv4,
yeah,
and BCDE is IPv6.
BCDE,
AF is IPv4 and BCDE.
but AF is also 4 and 6. It speaks both, right? No. Or BCDE speaks both. I'm not sure. So conceptually, it doesn't really matter what is encapsulated inside what, right? But there is one issue if you go through that other kind of tunnel, and that issue is that the flow ID might be lost. when you go from 6 to 4, because 4 doesn't have any notion of this flow ID. But you can still do the tunneling. You might lose some of the fields, but you can also do the you can still do the tunneling in the reverse direction.
What's the impact of TCP when you have to write a source and destination? What happens to that? I mean, does it change? Does it need to be?
So the TCP is talking between two IPv6 nodes. No change. So this is happening at the network layer. Another, maybe this is a good time to explain this concept. So if you understand this concept of tunnelings, have you heard of things called VPNs? Virtual private networks. So virtual private networks are networks, let's say, if you're telecommuting, your company lets you create a VPN connection between your home machine and your company network, and it's supposed to be secure. So imagine these IPv4 routers here as being the public internet. So your VPN is going over the public internet between your, let's say, home machine and the company network. You don't want the public internet to know anything about what you're doing. You don't want the public internet to see which packets are going where to which machine, no information. So you think of now you can think that the IPv6 connection is the connection between machines which are, let's say, your home machine and the private network of the company, which is not visible to the outside world. The tunnel is created over the public internet by encrypting your packets. They are encrypted, and then these packets are sent between the two gateways. So one gateway is on your home machine, the other gateway is sitting in front of the company network. Once the company network receives this packet, it can decrypt it and forward it along to wherever it was going. So now you see in this architecture, routers C and D did not have any knowledge about A, F, or what's inside. They did not have knowledge because they did not look under the data, or there's nothing preventing you from encrypting this entire data. So the public internet, which you can think of as this part of the tunnel, cannot look inside the packets. So VPNs are also kinds of tunnels in the same spirit. Yeah.
But V6, those B and E, and those systems, they have to have a V4 and a V6 address.
Yeah.
That's what.
Yeah.
And
So I mean, for these to coexist, there have to be some machines which speak both. Otherwise, they'll be completely different networks. There has to be some translation available some. There are some issues still debated about IPv6. One thing that somebody asked here was this address seems too long, 128 bits. I mean, is it giving us too large a space? Is it adding unnecessary overhead? Hop limit, there is a 65K, 16 bits assigned for hop limits. Again, seems completely unnecessary. On the other hand, the max packet size with IPv6 is still kept at 65K. Now this is not a very good idea because we're getting larger bandwidth networks, and for large bandwidth networks, you want larger packets. Larger packets will allow you to use the bandwidth much more efficiently, and your header to data ratio also moves favorably as we have larger packets. So for the same amount of processing, header processing, you can send a larger amount of data. So you have these high bandwidth long delay links, and on those links max packet size should be higher, but IPv6 never really addressed that. How do servers handle both types of packets? Again, you have to have dual stacks, and things get complicated as we saw. So if you've heard of IPsec, IP security, that's inbuilt with IPv6. And again, the implementation of IPsec is still an ongoing process. DNS is a big issue. DNS and IPv6 will be completely different from DNS and IPv4. How does DNS coexist? How do the two versions of DNS coexist? Because DNS is critical for any network to function. In fact, Columbia has machines which are running IPv6, and we even have an IPv6 DNS server. I think it's called bind.ipv6.columbia.edu. Columbia has, I can send you details of how the IPv6 network is running at Columbia. In fact, one of the last lectures of this class, I'm hoping to get the director of ASIS to come and give a talk and give an overview of what our network looks like, what are the services that we offer. Yeah.
DNS different IPv6 and IPv4 other than the address size?
Because they are sort of operating at in different spaces. Conceptually they are the same, but DNS running on IPv6 is different from DNS running on IPv4 because they're looking at different address spaces. And then there are issues of translation. If you have machines which talk both, should DNS be aware of that? To do things like tunneling. No, architecturally they are similar. But what all functionality should you build into the DNS? Should one DNS be aware of the other DNS? And if some name resolves to an IPv4 address and IPv6 address, how is that important? How can that be resolved or exploited? We'll look at multicast in the next lecture. We'll stop there.